We are now going to look at inverse trig functions. This is a concept that, on the one hand, is very straightforward. And when I briefly describe what inverse trig functions are, I think you'll find the concept pretty easy to grasp. But then at the same time, there's an aspect to inverse trig functions that then can make them a little complicated and a little tricky to use. So that probably doesn't make sense to be easy on the one hand, but then also to be tricky, but I think you'll see that that's the case. As a quick introduction to inverse trig functions, let's go back a minute and look at if we were given this very simple equation and we were asked to solve it. And let's just say we're going to only look at angles between starting at 0 and going less than 2 pi. So once again, we're going to be working with angles and radians. We've had this kind of problem before, and I want to emphasize, when I look at a problem like this, here's the question I ask in my mind. What is the angle? Could be more than one. What is the angle, or what are the angles where the cosine equals 1/2? Very straightforward. Now initially, all the angles we're going to talk about are special angles, and this is a special angle. So we could actually go to the unit circle and go see what are the angles where the cosine would be 1/2. So if you go unit circle, the cosine is always the x value. So I see right here, cosine's 1/2, so pi over 3. And I keep going. Here's negative 1/2, negative 1/2. Oh, sorry, I was looking at sine. Actually, right here. Here, the cosine is 1/2. So it looks like 5 pi over 3 and pi over 3. So there are actually two solutions. Now here's what's interesting. Let's look at the same kind of problem, but in terms of an inverse cosine function. So first of all, an inverse cosine function, you have a cosine, and then up here a superscript. Don't think of it as an exponent. Think of it as like a superscript. It's like a -1. That is the notation when we're talking about an inverse trig function. So in this case, this is inverse cosine. And inside the inverse cosine, you would have something like this. Now the interesting thing about an inverse cosine is an inverse cosine of anything is going to be an angle. And this is very important. Throughout the rest of this class, when we have problems where we deal with inverse trig functions, most of the time I will remind myself and say, here's an inverse trig function. A lot of times you'll see me right here. An inverse trig function is going to be an angle. That always helps me to solve a problem when I can conceptualize what's going on. So if you're given this problem, inverse cosine of 1/2 equals theta, once again, we want to know what is theta. Now what's interesting, when I see this inverse cosine function, here's the question I ask myself to determine this answer. I say, what is the angle where the cosine equals 1/2? Now if you notice, when I looked at this and tried to solve this equation for theta, and I was trying to find the angles, here's the question I ask. What's the angle or angles where the cosine equals 1/2? When I have an inverse cosine problem, the inverse cosine of 1/2 equals theta equals an angle. To get this answer, here's my question. What is the angle where the cosine equals 1/2? You know what? It's the same question. It's the same thought process. When I have something like this is what I ask myself. When I have an inverse cosine, it's the same exact question. So you might think, okay, what's the angle where the cosine equals 1/2? Just like up here, if we go one trip around the unit circle, so that would seem to make sense. Well, this is not quite right. And this is where inverse trig functions can get a little tricky. And I won't take the time to explain it. It's not really that important, but it's the whole idea of wanting to have one-to-one functions and all this kind of stuff. But here's what happens. Let me explain it this way. Let me sort of draw a unit circle here. For this first problem, pi over 3 and 5 pi over 3, both those angles, the cosine is 1/2. So now when I get to the inverse cosine, I ask the same question. Why would the answer to the inverse cosine problem not be the same thing? Well, there's a special rule about inverse trig functions. For inverse cosine, here's what happens. You are limited. The only angles that can be used for an inverse cosine function are the angles between 0 and pi. In other words, you would think 5 pi over 3 would also be an angle, but we're not allowed to use any angles on the bottom half of the unit circle. So that's the very important and unique property of inverse cosine functions. So, we're given this problem. What's the inverse cosine of negative square root of 2 over 2? In my head, I'm thinking this answer is going to be an angle. So I ask myself, what's the angle where the cosine is negative square root of 2 over 2? So I go to my unit circle, and I realize the cosine at 3 pi over 4 is negative square root of 2 over 2. Now you might also think, how about this angle here 5 pi over 4. But 5 pi over 4 is not in my allowed region. It's not in the part of the unit circle that I can get answers for inverse cosine problems. Just to make the point clear, if we were given this problem, cosine of theta equals negative square root of 2, what's the solution? I would in fact put 3 pi over 4 and 5 pi over 4. But we're not asking that. Whenever the problem is framed as an inverse cosine function, the only angles you can use are the top half of the unit circle. So there's only one angle. So that's a little different. So far I've talked about inverse cosine. So what happens if you have maybe we're asked what's the inverse sine of square root of 3 over 2. Here's where inverse trig functions even get a little more interesting. So I'm going to I'm looking for an angle where the sine is square root of 3 over 2. If you want to go to unit circle, where is the sine square root of 3 over 2? Well, right here at pi over 3, and here at 2 pi over 3. There's two angles in the unit circle where the sine is square root of 3 over 2. So once again, you would think your answer, you would have two angles However, just like inverse cosine has the special constraint where the angles have to be in the top half of the unit circle, you know what happens with inverse sines? So here's my unit circle. If we're talking about inverse sines, you know what? The only angles allowed are in the left half of the unit circle. So here's pi over 3, and here's 2 pi over 3. You know what? 2 pi over 3 is not allowed to be an answer for the inverse sine. So the inverse sine of square root of 3 over 2 is going to be pi over 3. There's only one angle that's going to be the answer. So far to summarize, inverse cosine, we're limited to half the unit circle for our answers, and it's the top half. So inverse sines, we're limited to half the unit circle, but it's actually the right half. And with inverse sines, there's an extra twist. Here, you know, so I drew the unit circle, 0, pi over 2, pi 3 pi over 2. So you would think maybe if we were asked what's the inverse sine of negative 1/2, well, you think unit circle. So now inverse sine, my angles have to be in the right half. So I look and I notice here the sine of 11 pi over 6 is negative 1/2. So you would think, okay, since we have this restriction, it's 11 pi over 6. that would seem to make sense. But you know what? That's not going to be the correct answer, even though you're probably thinking, like, what in the world? Well, here's what they do for inverse sine functions. Inverse cosine functions are nice because the possible angles go from 0 to pi, and it's all normal. Pi over 2 is up here. You know what they do for inverse sine functions? 0 is here, pi over 2 is here. However, any of the angles in this fourth quadrant, you know what they do? They don't call this 3 pi over 2. Instead, they start using negative angles. So 0 is here, negative pi over 2 is here. Remember, a negative angle is when you go clockwise. So therefore, this angle here is not 11 pi over 6 when we're talking about inverse sine functions. Instead, you think about this angle, negative pi over 6. Just like this up here is pi over 6. Well, we're going the same distance, but in the opposite direction. But if we're going to look at angles in this fourth quadrant, we want to have negative angles. So the inverse sine of negative 1/2 is negative pi over 6. So this is why inverse trig functions can get a little crazy at times, because inverse cosine problems, the angles, the answers have to be in the top half, and these are what we normally on the unit circle call those angles. We get to inverse sine, I'll draw it here, inverse sine angles come from the right half of the unit circle. And as it turns out, if we're down here in the fourth quadrant, we don't even use the unit circle angles. We decide to go and start using negative angles. So if I want to know what the inverse sine of negative square root of 2 over 2 is, I'm looking for an angle on the right half unit circle where the sine is negative square root of 2 over 2. It's actually going to be right here. Now for the normal unit circle, this is 7 pi over 4. But for inverse sines, we instead call this negative pi over 4. Now, the last thing we need to look at is, how about inverse tangent? Well, as it turns out, inverse tangents we treat the same way as inverse sines. So the angles for inverse tangents also have to come from the right half of the unit circle, and in the same way the angles are the same. In this fourth quadrant, the angles become negative. So for this one, inverse tangent of 1, we think, what's the angle over here where the tangent's 1? Well, that's going to happen when we have square root of 2 over square root of 2, and a positive 1. That's going to be pi over 4. However, what if we had the inverse tangent of negative square root of 3? So once again, you've got to think of tangent as sine over cosine. So for this one, we need an angle where, like, the sine is square root of 3 over 2, and the cosine's 1/2. and we need these to be opposite signs. One's positive, one's negative. That's going to occur in quadrant 4, and actually it occurs where the sign is this. We used to call this 5 pi over 3, but instead now we call it negative pi over 3. All right. So like I said earlier, inverse cosine, the concept I think started out not difficult to understand, but all these special constraints for inverse cosines, for inverse sines, inverse tangents, makes it start to get a little goofy. So when you do homework problems, the first homework problems are all going to be special angles, and they're all going to be pretty easy. Like I've listed some of these homework problems. What's the inverse sine of 0? The inverse sine says right half of the unit circle, looking for an angle where the sine is 0. Well, that occurs right here at 0 radians. Once again, this is an angle, like theta. It's going to be 0. How about inverse cosine of 0? Cosine says, all right, I'm looking for an angle where the cosine 0 has to come from the top half of the unit circle. Cosine is 0 up here at pi over 2. How about the inverse sine of negative 1? Inverse sine says I'm looking for an angle. When you take the sine of that angle, it's negative 1. Well, the sine is negative 1 down here. Now at the unit circle, we would want to call this 3 pi over 2, but it's an inverse sine function. We don't say 3 pi over 2. Instead, 3 pi over 2 is really the same thing as negative pi over 2, and that's what we're going to use. So really these inverse trig function problems are going to be pretty straightforward. Maybe I'll just do one more. I may have even already done this. Inverse cosine of negative square root of 3 over 2. So I'm looking in the top half of the unit circle. I'm looking for an angle where the cosine is negative square root of 3 over 2. Top half of the unit circle looks like here, square root is negative, the cosine is negative square root of 3 over 2. It's an angle of 5 pi over 6. Now there are going to be some problems where we actually are asked to find inverse trig functions of angles of non-special angles. So for instance, the first one I see here is once again, this is going to be an angle. I'm looking for the angle where the sine is 0.8. Well, that's not a special angle. But this actually is a pretty easy problem. In this case, you're going to grab your calculator. Now, you need to make sure it's in radians. See, right now, I don't know if you can see it, my calculator's in degrees. So now it's in radians. And you notice, for my calculator, hopefully you can see, here are my trig functions, sine, cosine, tangent. Let me move it up a little bit and focus. For this calculator, look at the yellow markings. So if right above the sine key, you notice it's inverse sine. Above the cosine is inverse cosine. Above the tangent is inverse. So these are inverse trig keys, which I access by hitting the yellow button. So if I hit the yellow button and then hit this button, it's actually going to do an inverse sine. So this problem I'm looking at says, what's the inverse sine of 0.8? So I'm going to enter 0.8, and then I'm going to go and execute the inverse sine, and it's like 0.93. Now the calculator is smart enough that it knows where the answers to inverse trig functions come from. In other words, what if I picked an angle in the fourth quadrant? Well, I can't pick an angle in the fourth quadrant. Let me state it like this. What if I did inverse sine of negative 0.8? You don't have to think about it too much because you just grab your calculator and so I'm going to put negative, I guess 0.8, negative, and then once again negative 0.927 or negative 0.93. So this angle is going to be up in the first quadrant. 0.93 is in here somewhere, 0.93 radians, because this is 0. Pi over 2 is like, around 1.6 radians. Down here is approximately negative 1.6 radians. So negative 0.93 is in here somewhere. But the bottom line is, if you're asked to find inverse trig functions of non-special angles, it's just a matter of using your calculator. So now let me say one last thing about inverse trig functions. Now this is how sometimes later on we're going to use them, and we have to be very careful. There will be times when we're trying to solve a problem and we're looking for the angle, and we'll have something like the tangent of theta equals 1.5, and we want to know what the angle is. Well, the way we're going to do this is a use for inverse trig functions. Let me take a minute to explain this. Let's go back to algebra. What if I was given this problem to solve? I want to know what x is. I have square root of x equals 3. Somehow, I need to get this from square root of x to x. Well, hopefully you remember from algebra, if you want to get rid of a square root, you sort of square it. Because a square root and something squared are like opposites. They sort of negate or cancel each other. Of course, you have to do it to both sides. So square root of x equals 3, you solve that, x equals 9. Well, we need to do the same thing here. We have tangent of theta equals 1.5, but I want to know what theta should be. Well, just like if I had a square root and I thought of like my x being stuck under the square root, the way I can, in a sense, get at the x is I square it, because when you square a square root, it cancels it out. How can I cancel out this tangent to get the angle by itself? You know what you do? you take inverse tangent of both sides. Because inverse tangent of the tangent, it's like these cancel out and you're left with the theta. So then you would grab your calculator, make sure I'm in the radian mode, and if I put in 1.5 and then hit inverse tangent, I would have like 0.98. So the angle's like 0.98 radians. So that's going to be another use down the road of inverse trig functions. So if you have you have some kind of problem where you've determined the sine of theta is negative 0.6, and I want to know what theta is. Well, what you can do is you can take the inverse sine of both sides. The inverse sine of the sine is theta. So now the inverse sine of 0.6, negative 0.6, is negative 0.64. All right, so inverse trig functions, pretty interesting. Sometimes they seem pretty simple, straightforward, but then you turn around and they can get pretty complicated. But I think the homework problems you have to do initially, you will not find very difficult.